Hello everyone and welcome back from Data Science Made Simple AI. In this lesson we're going to focus on one of the most fundamental neural network architectures, the multi-layer perceptron. Usually abbreviated as MLP. MLPs are important because they introduce many of these core ideas that appear throughout deep learning. We'll see how information moves through a feedforward network, how fully connected layers transform data, why activation functions such as ReLU are necessary, and how we can implement MLP using PyTorch. We also discussed the universal approximation theorem, which gives us an interesting theoretical perspective on what neural networks are capable of representing. And finally, we'll connect everything to actual training process by looking at the loss functions, optimizer, backpropagation, and the PyTorch training loop. So by end of this video, you should understand not only what the MLP looks like, but also how it learns. Let's begin with the basic idea of feed-forward network. MLPs are feed-forward networks. A multi-layer perceptron is a feed-forward neural network. The word feed-forward describes the direction in which information travels through the network. We begin with the input. The input passes through one or more hidden layers, and finally, the network generates an output. So conceptually, the flow is input, hidden layers, output. During this forward pass, information moves in the direction without recurrent loops. Let's take a practical example. Suppose we are building a neural network to predict whether a customer is likely to default on a loan. Our input features might include age, annual income, current credit score, and years of employment. We could represent one customer with a vector containing 5 numerical values. That vector enters in MLP. The first hidden layer transforms those original features into a new representation. The second hidden layer processes that representation again. Finally, the output layer produces the prediction. For example, if you are doing binary classification, the final network output may be a single numerical value called a logit. Later, we can convert that logit into a probability. An important feature of MLPs is that they usually expect fixed size input vector. That's one reason they're commonly used as a starting point for tabular data. For example, if every customer is represented by 10 features, every input entering in the network that does have the same position. Another important idea is that each hidden layer creates a new representation of data. The network isn't simply passing the original variables forward unchanged. Each layer transforms them. So we can think of MLP as a sequence of learned transformation. Original features, then hidden representation, number one, then another hidden representation, and finally the prediction. Now let's look at fundamental building block of MLP, the fully connected layer. A fully connected layer means that every neuron in one layer can connect to every neuron in the following layer. In PyTorch, we implement this using nn.Linear. Mathematically, a linear layer performs the transformation. Z equals W plus B. Here X represents the input vector, W represents the matrix of weights, and B represents the bias vector. The weights are extremely important because they determine how the network combines the input features. The bias give the transformation additional flexibility by shifting the output. Let's look at an example. Suppose our input contains 10 features, and the next hidden layer contains 64 neurons. In PyTorch, we would write nn.Linear 1064. That means the layer transform a 10-dimensional input into 64-dimensional hidden representation. If we are processing a batch of 32 observations, the input tensor might might have a shape 32 by 10. After this linear layer, its shape becomes 32 by 64. Now let's calculate the number of parameters. The weight matrix contains 64 times 10, which is 640 weights. Then we can calculate the hidden layer. Then we also have one bias for each of the 64 output neurons. We add 64 biases that give us 700 for trainable parameters. This is a very useful formula to remember for a fully connected layer. Number of parameters equal input futures time, output futures, plus output future for the biases. So the larger we make our hidden layers, the more trainable parameters the work contains. That gives the model more capacity, but it also increases memory requirements, computation, and potentially the risk of overfitting. This is one of the first architecture trade-offs we encounter in neural network engineering. Now we arrive at one of the most important concepts in neural networks, non-linearity. The fully connected layers we just discussed perform linear, or more precisely affine transformations. If we stack linear transformations without adding nonlinear activation function, the entire network can effectively collapse into one large linear transformation. For example, suppose we have several matrices W1, W2, and W3. If every layer only performs matrix multiplication, we can mathematically combine those matrices into another matrix. So adding more linear layers would not give us the expressive power that we expect from deep neural networks. This is why we introduce activation functions. The activation function shown here is ReLU, which stands for rectified linear unit. Its mathematical definition is extremely simple. ReLU is x equals the maximum between 0 and x. That means if the input is negative, ReLU returns 0. If the input is positive, ReLU keeps the original value. For example, negative 5 becomes 0, negative 1 becomes 0, 0 remains 0, 2 remains 2, 8 remains 8. So ReLU transforms the vector negative 5, negative 1, 0, 2, 8 into 0, 0, 0, 0 to 8. Despite its simplicity, this operation is extremely important because it introduces nonlinearity into the network. That allows multiple layers to combine and represent much more complex relationships. For example, imagine we are trying to predict the customer behavior. The relationship between income, age, debt, and probability of default is unlikely to be perfectly linear. There may be thresholds, interaction, and complex combinations. Nonlinear activation functions allow the network to model those kinds of relationships. ReLU is computationally inexpensive, which is one reason it became so widely used. However, ReLU does not have some limitation. One famous issue is known as the dying ReLU problem. If a neuron consistently receives negative inputs, ReLU always outputs 0. Its gradient in that region can also remain 0, meaning that neuron may effectively stop contributing to learning. Other activation functions, such as likely ReLU, GLU, and SILU, can sometimes address different limitations, but ReLU remains an excellent activation function for understanding the basic mechanics of MLPs. Okay, now let's translate the architecture into actual PyTorch code. We start by defining a class called simple MLP. our class inherits from NL module. This is important because NN module is the fundamental base class used to build neural network in PyTorch. It gives us access to functionality such as parameter registration, moving the model between CPU and GPU, saving model states, and switching between training and evaluation behavior. Inside the constructor, we define three fully collected layers. Okay, this is the three. Okay, the first one is FC1. It transforms the input sides into hidden sides. The second one, FC2, takes the hidden representation, produces another hidden representation of the same sides. The third layer, FC3, maps the hidden representation into the final output sites. We also create a ReLU activation. So the architecture is linear, ReLU, linear, ReLU, linear. Okay? Now let's look at the forward method. This method defines how information move through the network. First, we compute self FC1 x. Then we immediately apply ReLU. So mathematically H1 equals ReLU of W1 plus x plus B1. Next, we pass that representation through the second fully connected layer and apply ReLU again. So H2 equals ReLU of W2 H1 plus B2. Finally, we pass the result through the output layer. Notice something important. We do not apply ReLU after the final layer. The output layer returns the raw network outputs. For classification, these raw values are often called logits. For example, in a binary classification problem, the model may output a value such as 2.4. That number is not directly a probability. We could apply a sigmoid function and transform it into a value between 0 and 1. However, when using a PyTorch BCE with logits loss, we normally leave the model output as raw logits because that loss functions and the function sigmoid, in this case, the sigmoid transformation, internally in a numerically stable way. So architecture is intentionally separated from the final probability transformation. That's an important PyTorch design pattern. Now let's step away from implementation for a moment and discuss one of the most interesting theoretical results associated with MLPs, the universal approximation theorem. In simplified terms, the theorem tells us that a neural network contains at least one sufficiently large hidden layer and an appropriate nonlinear activation function can approximate a very broad class of continuous functions. Imagine that the true relationship we want to learn is some complicated function. Perhaps the output changes with several curves, thresholds, and interactions. The universal approximation theorem tells us that theoretically the MLP can represent that function with arbitrary accuracy under appropriate mathematical condition. This sounds incredibly powerful, but we need to understand what the theorem does not tell us. It doesn't tell us how many neurons we need. It doesn't tell us which architecture will train efficiently. It doesn't guarantee that gradient descent will find the correct weights. It doesn't guarantee that the model will generalize to unseen data. and it doesn't guarantee that the model will be computationally practical. This distinction is fundamental. Representational capacity is not the same thing as trainability. We can imagine the space of all possible neural network parameters as an enormous multidimensional landscape. Somewhere in that space, there may be an excellent configuration of weights, but finding that configuration is the difficult part. That's where architecture design, optimization algorithms, learning rates, initialization strategies, training data, regularization, and the many other engineering decisions become important. So the universal approximation theorem explains the potential of our neural networks. Training determines whether we can actually realize that potential. Now you analyze the three components of training. Let's look the different part: loss function, optimizer, training loop. This is the major components shown in these slides, substantially: loss function, the optimizer, and training loop. And we want to talk about the loss function. Loss function measures how different the model's predictions are from the correct answers. For regression, one common choice is mean squared error, or MSE. Suppose the correct values are 10 and 20, while our prediction are 12 and 17. Our error are plus 2 and minus 3. The square, we square those errors, which give us 4 and 9. Then we calculate their mean. So the mean squared error is 6.5. The objective on training is generally to reduce this loss. For binary classification, PyTorch provides BCE with the logits loss. BCE stands for binary cross entropy. This is appropriate for problems such as fraud versus legitimate, spam versus no spam, default versus no default. The model produces raw logits, and the loss function evaluates how well those logits correspond to the true binary targets. The second component is optimizer. In this example, we are using Adam. The optimizer receives the model parameters and the learning rate. The learning rate here is 0.001. The optimizer job is to use gradients to decide how the network parameters should change. You can think of the gradient as telling us which direction changes the loss. The optimizer then uses that information to update the weights. Adam is more sophisticated than basic gradient descent because it keeps adaptive statistics about the previous gradients. But conceptually, the objective remains the same: modify the parameters so that the loss decreases. PyTorch training loop. PyTorch training loop. This part represents the operational heart of neural network trainings. Let's walk through the complete sequence. First, we receive a batch of training example. For example, instead of processing 100,000 training samples simultaneously, we might process 32 or 64 examples at a time. This is called the mini batch training. Next, we perform the forward pass prediction, model batch X. The input passes through all of our layers and produces predictions. Then we calculate the loss FM prediction batch Y. This tells us how wrong our predictions are compared with the true labels. Now we need to calculate the gradients. But therefore, before doing that, we call optimizer 0 grad. This is important. This is important because PyTorch accumulates gradients by default. If we don't clear the previous gradients, the gradients for multiple batches will be added together. Then we call loss backward. This performs backpropagation. PyTorch automatically calculates how the loss depends on every trainable parameter in the network. In mathematical terms, we are calculating derivatives such as the derivative of the loss with respect to each weight. When this gradients exist, we call optimizer step. This is the line that actually updates the parameters. So be careful with an important distinction. Model train does not itself update the weights. Model train simply puts modules such as dropout and batch normalization into their training behavior. The actual parameter update happens when we call optimizer point step. Then we move to the next batch and repeat the process. So the cycle is forward pass, loss, zero gradients, backward pass, optimizer step. We repeat this for every batch. When we have processed the complete training dataset once, we completed one epoch. If we train for 50 epoch, the network goes through the training dataset 50 times, usually seeing the samples in different shuffled batches. Why do we use mini batches rather than processing the entire dataset at once? One reason is memory. A large dataset may not fit into RAM or GPU memory. Mini batches also allow us to update the model more frequently. Instead of waiting until we have processed 1 million examples before updating the weights, we can update them every 32, 64, 128 examples. This creates a balance between computational efficiency and useful gradient estimates. Okay, we are at the end this lesson. Some key takeaways. Let's bring everything together. The first concept to remember is feed-forward flow. In an MLP, information moves from the input through hidden layers and eventually reaches the output. Second, the MLP rely heavily on fully connected layers. PyTorch and nn.Linear learns both a weight matrix and a bias vector. These parameters determine how information is transformed from one layer to the next. Third, we need nonlinear activation functions. ReLU is a classical example. Without nonlinearity, stacking multiple linear layers would not give us the expressive power we associate with the deep neural network. Fourth, we have a training process. The model performs a forward pass. We calculate a loss, backpropagation computes the gradients, the optimizer updates the parameters, and then the process repeats. So one pipeline summarizes the architecture. Input, linear, ReLU output. And another pipeline summarizes learning, forward, loss, backward, update. Finally, remember what we learned from the universal approximation theorem. An MLP can theoretically represent extremely complex functions, but the theoretical capacity does not automatically give us a successful machine learning system. In practice, success depends on the architecture, the quality and quantity of data, the loss function, the optimizer, the learning rate, regularization, training strategy, and the ability of the model to generalize to data. It has been seen before. This is one of the most important lessons in deep learning. Neural networks are powerful not simply because they contain many parameters, but because we have a method for learning a useful configuration of those parameters from data. And understanding the MLP gives us the foundation we need before moving on to more specialized architectures such as convolutional neural network, recurrent neural network, and transformers. Thank you for watching, and you'll see in the next lesson. See you soon from Data Science Made Simple. Have a great repeat of this lesson and watch again this lesson. Bye.